Okay, it's Brian, and I'm back here for another installment of talking about quantum mechanics or quantum physics. This is day number 2, and we're going to continue more or less where we left off. But before I do that, I want to do an installment of things I like about your generation. And I've done this when I met with you in person, and I thought, I need to do it now more than ever. And I want to tell you this. I'm so sad that I'm not getting a chance to meet with you folks in person. But if I had to pick a generation of students who could deal with the kinds of uncertainties and the disruption and the changing way of doing things, I think it's your generation. You guys flex with things. You're really good at that. You're really flexible. You kind of like understand the point of what you're trying to do and are willing to adapt to a different way of making it happen. So I've been very pleased with how seamlessly you folks have made this transition. So props to you guys. Thank you for that. Now, last time we talked about the crux of the quantum biscuit, and I want to particularly think about this piece right here. Particles have this wave nature, and confining them restricts them to certain energy states. That means the energy is quantized. So the wavishness of particles leads to the quantization of energy, and that's a weird notion. But it really leads to this quantization, really important. Particles have this wave nature. And so because now I want to come back and consider this wave nature of particles again. Here's how we compute the wavelength of particles. Planck's constant divided by m. That if I have lower speeds is going to correspond to longer wavelengths. I have that wave nature. It corresponds to V. And I want to ask you some questions about this. Suppose you took an electron and accelerated it from rest through an 8,000 volt potential difference. My question is this: by what factor would the wavelength increase if they were instead accelerated through a 2,000 volt potential difference? And I want you to solve this not by doing calculations. I want you to solve this doing the ratio reasoning that we've talked about. Don't plug numbers in your calculator. Go ahead and just look at ratios. How will this work? I want you to pause. I want you to compute, and then we'll come back. Well, when you accelerate the electrons through a potential difference, the amount of change in potential energy they have is equal to their kinetic energy. And the kinetic energy is 1/2 mv squared. So if I took the potential difference and I decreased it by a factor of 4, what that means is I've decreased the kinetic energy by a factor of 4. And if that's true, since the kinetic energy is proportional to the square of the velocity, if the kinetic energy goes down by a factor of 4, the velocity goes down by a factor of 2. And so we know that's true because it's v squared. And so if I have squared the velocity, which goes down by a factor of 2, that gives me an overall reduction of kinetic energy by a factor of 4. So if I took this number in the denominator and I decreased it by a factor of 2, what that does is that increases the wavelength by a factor of 2. So the wavelength will increase by a factor of 2. And I solve my de Broglie wavelength relation. And if I take doing ratios, okay, and I want you to make sure you can solve it that way. If I look back, particle. Now, I want to talk about this fact, okay? It's true in some sort of a gas and I cool them down, the speed that they're moving at decreases with temperature. So decreasing temperature corresponds to decreasing speed, and decreasing speed corresponds to increasing wavelength. And this is really important. I want you to think about this. We're going to talk about this thing called a Bose-Einstein condensate. So in one particular case, a gas consisting of atoms of sodium-23 was cooled down to 200 nanokelvin. And I want you to calculate, for that case, the de Broglie wavelength. And given that, I want you to compare it to the diameter of the atoms and see what you get. And we'll see where this takes us. And it's going to take us into the range of the Bose-Einstein condensate, which is kind of a crazy thing. And these experiments were done in the 1990s. These were done while I was at Colorado State University. It's one of the most modern things we'll talk about in this class. Super, super exciting. Super cool. The mass of sodium-23, of course, is just 23 atomic mass units. You know that that's true. The RMS speed is given by this relationship right here. That was something we learned in chapter 12. I want you to put all the pieces together, and I want you to calculate what is the de Broglie wavelength. Oh yeah, and this Boltzmann's constant Boltzmann's constant K times B, that's this constant right here. We learned that back in chapter 12. So I want you to pause. I want you to do a calculation. I want you to assess your results before going on. You complete your calculation for this. What you find out is this: the particles are moving at a breathtakingly slow 14 millimeters a second. I want you to compare that to the typical atomic speeds that we'd seen previously of hundreds of meters per second. Very, very slow. And that means they have a very, very long de Broglie wavelength, 1.2 microns. What? That's significantly larger than the 0.36 nanometer diameter of the atoms, significantly larger. And it turns out, because the wavelength is so big, the smeared outness of the atoms is significantly bigger than the size of the atoms. They look like this just fuzzy wave function. And it turns out that wave functions are so big, if you can make a cold gas of atoms and you can get enough atoms in that gas, their de Broglie wavelengths start to overlap, and they make this thing called this Bose-Einstein condensate. Crazy new state of matter that won the Nobel Prize for some folks from the University of Colorado down in Boulder, where all the particles have a tendency to want to go into the same quantum state. And so what they'll do is this. This is basically a picture of a Bose-Einstein condensate developing. So I have this gas of atoms, and they're spread out. And then as they start to overlap, certain kinds of atoms called bosons, and they have a certain number of spins. Don't worry about the details. They want to overlap. And so as a consequence, once they start to overlap, they like that, and they overlap more and more and make this very, very tightly peaked function. And they make basically a single atom that's composed of thousands of particles. It's like a superatom. So this is a little structure that is a whole bunch of atoms, each of which has a certain wavelength associated with it on top of each other. So it's like thousands of atoms with all of their wave functions overlap. So it's not a gas consisting of 1,000 atoms. It's a wave consisting of a whole bunch of atoms on top of each other with their identities indistinct from each other. You're going to have thousands of things in the same place at the same time, which is crazy, crazy, but real. Cuteness right here. That's what sodium atoms want to do. Not as cute, but they want to overlap. They want to be in a pile of puppies. They want to be all in one place at one time. That's the Bose-Einstein. Not too long of particles in one place at one time, which is, I think of it like puppies. Puppies want to be overlapping. They're happiest when they're like overlapping with other puppies. You know they like this. Look at that pile of puppies. Look at that exercise. Now, you can have if you can have multiple particles being in one place at one time, that's weird. But you can also have a single particle be in two places at one time. You've seen this before. You've seen p orbitals that look like this. This is a picture of where you find the electrons. You find them here, and you find them here. They are never, ever, ever in the middle. And so really, some of the reality of the electron is over here in this lobe. Some of it's here. It is split. It's in two places at one time. Some of the reality of the electron is in one place. Some is in the other. That is a real thing about cause of this little particle be in two places at one time, which in physics, that's kind of crazy. And this is disturbing, and some of the early architects of quantum mechanics didn't like this. Niels Bohr You're familiar with like the Bohr atom. Anyone who's not shocked by quantum theory has not understood it. Erwin Schrödinger of the Schrödinger equation liked it even less. I regret I ever had anything to do with quantum theory. Even Albert Einstein, who won a Nobel Prize for his discovery or his elucidation of the photoelectric effect, said quantum mechanics is imposing, but it is not yet the real thing. Didn't like it. The architects of quantum mechanics didn't like it. It's weird, bizarre. We need to talk about the philosophical notions here, and I will post a little thing where I talk about the philosophy. I won't say more about it now, but offline I encourage you to take a look at this little thing. And I'm sorry I can't deliver it in person, but it's one of my favorite things to talk about. Now, we've seen that the wave nature of particles leads to quantization. We talked about the particle in a box, and I want to do a... So we've seen that the wave nature of particles leads to quantization, and we talked about this with the particle in a box. Specific case of this. Okay, you can only get certain possible. I'm going to take a look at, and here was like our particle in a box, kind of like system of levels and the possible transitions. I want to take transitions. And we've seen this previously. We've seen this quantum system when we looked at what possible energies could be emitted by this system. But now I want to say, rather than looking at the maximum and the minimum, I want to look at all the possible energies that could be emitted. Look at the problem that we had last time. We looked at this system, and the question was, what was the maximum and minimum possible energies of photons that could be emitted? But now I want to look at all possible energies. What energy photons could come from this system? I want you to go ahead and take a minute. I want you to pause, do some calculations, then we'll continue. That previously, well, anytime I've got one state where a particle could be and it can transition to another state, I can have a possible emission of a photon. So I can have an emission from when an electron drops from n equals 4 to n equals 1, or n is equal to 3 to 1, or 2 to 1, or 4 to 2, or 3 to 2, or 4 to 3. Those are my possible transitions, and those correspond to this suite of energies. That's what the spectrum of this, if this was like a gas and we electrically excited it, that's what wavelengths we would find in the spectrum. But I want to come back to this question of dye colors. And it turns out some particularly bright dyes, like the dye that was made to make this bowl, use basically a quantum looking at dye colors. We want to know what colors are being absorbed by that dye. And if we know what colors are being absorbed, we can say something about the color that, and they use a system where I've got long chain molecules, and the electron can exist somewhere along the chain. So take a look at this. There's a chain of carbon atoms here, okay, and the electron can be anywhere along that chain, but it's repelled by the nitrogen-containing rings at the end. So what that means is, electron, you can't go any farther than here, and you can't go any farther than here, but you can exist anywhere along here that you'd like. So that looks like a particle in a box. And so that particle in a box model, which we saw previously, actually applies in this case. So we have this situation. In this case, the box is about 0.75 nanometers long. We are peers. Here's my question, okay? Modeling this as a particle in a box, what are the 4 lowest energy levels? 2, what are the 3 lowest photon energies that could be absorbed? And then third, what is the longest visible light wavelength in the absorption spectrum? And if we're looking at dye color, I want you to look back for the particle in a box energy model, figure out the lowest 4 energy levels, figure out the lowest 3 photon energies, and then answer this question right here. That's the one we're interested in. Since we're interested in the dye, what's the longest visible light wavelength in the absorption spectrum? Now, there's a lot of calculating that has to be done here. So I want you to pause. I want you to pull out your calculator or a piece of paper or however you work. I want you to complete this calculation and do not go on until you have definitive results that you can assess. So go ahead and calculate. We'll be back. Now remember, you do the calculation of the energy levels of the particle in a box this way. That's the energy of the nth state. And I was told to find the 4 lowest energy levels. So for n, I'm going to choose n is equal to 1 and 2 and 3 and 4. If I take that expression in the brackets, h squared over 8 times m times L, that's an energy. So I'm going to go ahead and calculate that expression first. That's an energy. And you're going to calculate it in joules, because you're going to take h in joules times seconds. And we have to do that because I'm dividing by m and I'm dividing by L. And so I'm going to need kilograms, meters, seconds, all that. I'm going to need the SI units. So I take h, I put it in joules, I calculate, and then I'm going to take that result and I'm going to convert it to electron volts, because ultimately I want to work in electron volts. So if I do that, I take that whole expression in brackets and I convert it and I put it in joules. I'm sorry, I compute it in joules. If I convert it to electron volts, the whole expression in brackets comes out to be 0.67 electron volts. So I can compute it in joules, I convert it to electron volts, and so it's this. So the energy of the nth state is 0.67 electron volts times n squared, where n has the values of 0, I'm sorry, not 0. That's not an option, Brian, you scamp, of 1 and 2 and 3 and 4. With those in hand, I can calculate the lowest 3 photon energies. So if you haven't done this, take this expression, there's my energy levels. I get the energy of the nth state, 0.67 electron volts times n squared. Compute the lowest 4 energy levels, and then compute the lowest 3 photon energies that could be absorbed, and then think about this, the longest visible light wavelength in the absorption spectrum. So I want you to stop. I want you to calculate. Now, if you've already done it, go on. But some of you didn't, you little scamps. You just jumped ahead. And so I'm giving you more detail. So now I want you to, honest to goodness, pause, do a calculation. Do a calculation for the lowest energy levels. Look at the photon energies, and then compute this. Finish your calculation. Assess your results. Then we'll come back together as a class. Now here's what I get. For the lowest 4 energy levels, I get 0.67 electron volts, 2.68, 6.03, and 10.72. If I look at the lowest 3 photon energies, those correspond to photons, electrons going from n is equal to 1 into higher energy levels. So it can go from n equals 1 to n equals 2, or from n equals 1 to n equals 3, or n equals 1 to n equals 4. And so I get those possible transitions. And those correspond to energies of 2.01, 5.36, and 10.05 electron volts, which correspond to the wavelength of photons of 620 nanometers, 231, and 123. The only one in the visible light region of the spectrum is this one, 620 nanometers, and that's kind of in the red-yellow region of the spectrum. So if I look at that bowl uses this very dye. When light hits it, the reds, the yellows are the results of my calculation. And so as a consequence, what color is left? Blue-green. It absorbs the reds and the yellows. It doesn't absorb the blues and the greens, and so you end up having kind of a blue-green dye. That's how you do it. You get very, very bright colors with this kind of dye. So my assessment is everything's good. The color even matched. Now, here's a question for you. If you increase the length of the chain, how would that affect the wavelength of light absorbed by the dye? And there's a few steps here, and I want you to think it through, and I want you to do it by ratio reasoning. Here's the values of the energy levels. What happens to those if I increase the length of the box? And how will that change the wavelengths absorbed? By the way, I'm coughing. That's not the coronavirus. I just swallowed a little bit wrong. So I'm going to give you a moment to pause and think about that. And I want you to honest to goodness pause. I want you to honest to goodness do that calculation. I want you to honest to goodness not think that Brian has the virus, but just think Brian needs a moment to rest his voice. And during that moment, I want you to be doing some calculation. So go ahead and do that. I'll be back. Now, if I've increased the length of the box, this has gone up, the values of the energy states have gone down. And so instead of having levels spaced by a large amount, I will have levels spaced by a smaller amount. What that's going to do is going to decrease the energy difference when electrons drop from one state into another. So if I decrease the energy of the electrons, the energy difference, I'm going to decrease the energy of the photons. If I decrease the photon energy, I'm going to increase the wavelength. And so I'm going to see an increase in wavelength, and so I'm going to get different colors of dye. And in fact, that's how you would make different colors of the dyes. Just change the length of the box, and if you do that, you can change the color. Now, what would happen to the energy levels if we made the box really, really, really small? So if the box is tiny, so if L is tiny, the energy levels, in fact, are going to be huge. And that's why if I take protons and neutrons and force them to exist inside the confines of the nucleus, I end up with really, really huge energy levels. And that's why nuclear physics has a completely different energy scale, as we're going to see next week when we talk about things. The reason that constraining particles to tiny, tiny, tiny boxes gives them really large energy here. But I want you to do a quick calculation for this. So suppose I took a proton and I force it to exist inside a nucleus, and the diameter of the nucleus is about 10 Fermis, or femtometers, 1 × 10 to the negative 15th meters. Okay, here's my question. What's the kinetic energy of the proton if its de Broglie wavelength is this much? So if I took the particle and I constrain it, it's got a wavelength which is smaller and smaller and smaller, and smaller wavelengths corresponds to higher and higher energies. And just to see this, and to see another ways, is to finish this calculation, which I want you to do. I want you to pause right now. I want you to pull out the calculator, complete this calculation, assess your results, then we'll come back together as a class. So the first piece of the puzzle that you'll do is this. You're going to compute the kinetic energy of the proton. You're going to say the kinetic energy. You're looking for the kinetic energy of the proton. I'm going to get the kinetic energy by getting the speed, because the kinetic energy is 1/2 mv². I'm going to get the speed by looking at my relationship for the de Broglie wavelength. The wavelength is h over m times v. So if I've been given lambda, I can calculate v. Given v, I can calculate the kinetic energy. I can take that and convert it into electron volts, and I get a value of 8.3 million electron volts. And so the energy is very high. And so the energy of the constrained particles inside a box the size of the nucleus is very large indeed. And that's why nuclear physics has an energy scale that is so large, which will be something we talk about Heisenberg next week. Now, another concept I want to talk about with quantum mechanics is this idea of the uncertainty principle. And the uncertainty in the position of a particle times the uncertainty in its momentum is greater than or equal to some constant. So what that means is this: if you improve your knowledge of the position, you decrease your knowledge of the momentum, and i.e. the speed. You can't precisely measure both the position and the speed of a particle. You can't measure them both with arbitrary accuracy at the same time, and that's this uncertainty principle. And this has uncertainty principle that the product of the uncertainty in position times the uncertainty in the momentum is greater than a certain quantity. So if I decrease delta x, if I measure a position more precisely, I increase the uncertainty. If you measured all the positions, you have destroyed your ability to know delta v and practical implications. If you take a particle and you know precisely where it is. You know where it is. You don't know where it's going. You don't know where it's going. The uncertainty in the speed is proportional to 1 over the uncertainty in the position. So here's 3 wave functions of particles. Here's one that's pretty spread out. Delta x is pretty big. I don't know where that particle is, and so I can know where it's going. Here's an intermediate case. There's a final case where the wave function is very sharply peaked. That means it's a tiny little wave function with a tiny value of delta x. I know where that particle is compared to this one up here, which is really spread out. I don't know where that one is. So the first one, I don't know where it is. I can know where it's going. The third one, I do know where it is. I can't know where it's going. And so as it travels, it will spread out more. And we can see this. And if you look at the first, where the particles are right now, and then I look where they are subsequently, we can see that as the particles move, they will spread out. And the one that spreads out the most is the one that is most accurately located. So here's where the particles are now. Then illustrate speed, and so precisely sometime later they look like this. And you can see the particle that we knew where it was is now spread out like crazy, and the one that we didn't know where it is has not spread out nearly as much. This of these particular wave functions, I take a particle and I localize it and then I let it go, it's just going to spread out. Able to know delta measure the position is something that we made into a little video of wave function evolution. You can look at the evolutions. I want you to pause and take a look at that video and you can see, but it boils down to this more. Now, this has practical implications, and I want to think about this. Okay, if an electron is associated with a particular atom, that limits its uncertainty in position to 1 nanometer. It's somewhere inside a box that's centered on this atom. And so we're going to assume that means it's delta x. The width of its wave function basically can't be more than about a nanometer or so. What uncertainty in speed does that imply for the electron, since we've constrained it to be next to an atom? I want you to calculate that. So pause for a minute, calculate, and we'll be back. And of course, the way you calculate that is this. The uncertainty in the position times the uncertainty in the momentum is greater than or equal to h over 4 pi. Okay? So the uncertainty in the position, well, that's just 1 nanometer. The uncertainty in the momentum, that's m times delta v. Okay? The mass is not uncertain. An electron has a certain mass. And so the uncertainty in the momentum is m times delta v. Delta v is the uncertainty in the velocity. That's the number that we're looking for. With that relationship to hand, we can do a calculation made precisely. And if we complete it, we get an uncertainty in speed of 6 times 10 to the 4th meters per second. So because we've made an electron exist in the vicinity of an atom, we've set its uncertainty in position is 1 nanometer. We don't know its speed greater than plus or minus 60,000 meters per second, 60 kilometers per second. That's here to Longmont in 1 second. So basically, if we know where the electron is, we have absolutely no idea where it's going. And so as a consequence, we draw these pictures of atoms, not like, oh, here's my nice little nucleus, and here's my orbits of electrons around them like so. We don't draw these comforting diagrams I had back when I was a child. Oh, heavens to Betsy, no. Now we draw these kind of like fuzzy, crazy diagrams where the electrons exist in this kind of like very, very fuzzy kind of like reality. They're smeared out because we have some sense as to where they are, but we have no idea where they're going. So as a consequence, we can't localize them more precisely than that. You can. Now, this also relates to some science fiction things. Suppose, like they did on Star Trek, you were to beam somebody. And so you're going to beam somebody. You're going to put them in the transporter, beam them someplace. If you listen to them talk about what beaming means, what it means is we take all the atoms in your body, we measure where they are, and then we send them in a beam to someplace else. Well, if the first piece of the puzzle is you measure where the atoms are, you know where they are, you know delta going, so I measure where they are. As a consequence, I can't know where they're going. And so beaming someone is not a thing. But here's the thing. If you look at Star Trek The Next Generation, the people who worked on it knew their stuff. They knew their stuff. And there's a clip of this show, which I like to show in class, and I can't show videos on this format, and there's also fair use guidelines. And so I'm just going to do a little voiceover for it. But it's this scene, and if you order can't work, and this is a plot where all the atoms, and you're in this is like in the holodeck, and there's Moriarty, and Moriarty is involved with this woman, and Moriarty is the evil character from the Sherlock Holmes mysteries. Anyway, he's a fictional character. He's on the holodeck. And Picard is saying to her, so we have discovered you want to leave the holodeck with Moriarty. And she says, oh yes, more than anything. And he says, we have discovered that if you decouple the transporter's Heisenberg compensators, we can do something. I don't remember the exact details. But here's the thing. He's talking about Heisenberg compensators in the transporter. So what that means is he's acknowledging the existence of the Heisenberg uncertainty principle. Picard knows, well, Picard, the fictional character of Picard knows. Who knows about Patrick Stewart? Knows that there's this thing called the Heisenberg uncertainty principle that says that feature in a major network television show, which is fantastic. And so when I saw that, I said, oh my gosh, there was one of my people worked in that show, and I am so happy about it. But this Heisenberg uncertainty principle and the limitation on your knowledge is part and parcel of the weirdness of quantum mechanics I want to talk about. But now I want to give you a chance to think about the homework assignments, and based on the homework assignment, which you have plenty of information to solve now, we're going to go and look at applying these quantum principles to some practical situations. I want to look at the concepts of fluorescence and phosphorescence and bioluminescence. And that's what I'll talk about in the next installment. Thanks very much.